Good evening, students. Am I audible to all?
Yes, sir. Yes, sir.
Thank you. Thank you, Abrar. So we have taken we have two classes of your PGDSC paper 4 MCH-004 paper, and we have completed your block 1 of unit 1, 2, 3, that is basic of electrochemistry, electroanalytical methods, followed by potentiometer, and under the potentiometer we have discussed pH metry, and the last part we have discussed, that is the conductometer, or that is related to your conductance. And today we will move forward to our next part, that is your unit 5. It in uh, it is electrogravimetry and coulometry, electro analytical method. So before that, we have already discussed the basic parameters of electrochemistry, like what is conductance, what is resistance, the relation between both of them. Then we have specific resistance, specific conductance, followed by what is equivalent conductance, molar conductance. Like this, we have discussed. And under potentiometry, we have discussed electrochemical cell, galvanic cell, voltaic cell, then followed by your Nernst equation, and pH. In pH metry, we have discussed what is pH, how pH affects the conductance or the potential of a cell, and we have some free energy relation, that is del G equal to minus epsilon K, or del G equal to minus NFE, then followed by your conductivity or conductometry titration. So these things we have already covered up. Let's we have today's class, that is unit 5, electrogravimetry and coulometry. So now I am sharing my screen with you. I think uh, the PPT is very much visible to you all.
Yes, sir.
Okay, okay, okay,
Yes, sir.
okay, okay, okay. So this is your unit 5 and 6. Unit 5 involve your electrogravimetry, and unit 6 is your application of electrogravimetry, coulometric and conductometric application to different mm, field of chemistry, and this involve your block 2 unit 5 and 6. So let's have the basic part of electrogravimetry. So it is a method used to separate and quantify ions of a substance, usually a metal. It is a method for the separation of metal ion by using electrodes. So here what happen, generally platinum electrode is used as both cathode and anode. So anode is platinum and cathode is also platinum, but the electricity supplied, that is of different potentials to different electrodes. That is the potential difference between platinum anode and platinum cathode, that is generally 6 volt or something like that. So here the electrode applied, both are noble metals or neutral electrodes. Generally platinum is used. So here what happen, uh, the metal in the solution, that is in the electrolyte, is separated at cathode, and this cathode, that is platinum cathode, is weight before the analysis and after the analysis. So the difference in weight of the platinum platinum electrode, that is your platinum electrode is the amount of sample or amount of metal present in the solution. So that is your so this is a gravimetric estimation or by weight estimation of the metal present in the sample solution. So electrochemical reduction causes the analyte to be deposited on the cathode. The deposition takes place on the one electrode, that is at the cathodic electrode. The mass of the cathode is determined before and after the experiment, and the difference is used to calculate the mass of the analyte in the original sample. This gives the amount of metal present in the given solution. So we have to weight the before weight and the after weight of the electrode, and the mass difference will be the mass of the metal present in the sample solution. The weight of this electrode is determined before and after the deposition. By controlling the potential, this is very important. By controlling the potential, uh, is to ensure that only metal being analyzed will be deposited on the electrode. So this controlling of potential is done with the help of a register, or this is known as um, your difference in potential. So it is used for the for determination of concentration of chemical element very accurately and precisely in quantitative measurement. And we have in a solution the different species are separated by selectively plating out and removing out. It is used to electrochemical method for removing interferences. So these are some applications of electrochemical. So this is the principle where this is known as a platinum gauge. This is just a net like structure of a platinum. Okay, so this is known as, this is the cathode. This is platinum gauge cathode, and this is acts as the cathode, and the anode is a platinum wire or the spiral anode. This is just a spiral anode, that is the platinum. It is also the platinum. So these both are connected through external electricity. Here it is a battery, and the current is measured with the help of this ammeter. So this is the um, instrumentation of your electrogravimetric apparatus, where the metal is dissolved in a solvent to prepare the solution. This is the sample solution in a gray color, and we have the net like platinum structure. This is known as platinum gauge. This is the cathode, and this platinum wire is the anode. So we have connect the platinum cathode and platinum anode to the external battery, and we have some potential difference here. And by applying the electricity, what happen? The metal from this sample solution or analyte solution will be deposited on the cathode, and the difference in weight of this cathode will be the amount of or quantity of metal present in the solution. This is mainly done in industrial purposes, where the gravimetric or by weight determination of metal in a sample is needed. Then we have the metal is deposited by means of potential application. The electrodes are transported to electrode by the following mechanism, that is diffusion, migration, and convection. So these three are the mechanistic steps which involve in electrogravimetry. Then what is the difference between electrogravimetry and coulometry? So for in electrogravimetry, the product is weight as a deposit on one of the electrode. But in coulometry, the quantity of electricity needed to complete the electrolysis is measured as coulomb. So this is coulometry. This means it is the measurement of electricity in terms of coulomb. Like 1 Faraday equal to 96500 coulomb. So we have to measure how or what is the quantity of electricity that will be needed to complete the chemical reaction, that is through your coulometry. So this is just we can say this is just the replacement or an alternative to our ammeter. that is what is the amount of current passed through it, it is multiplied by time, it will give the electricity, that is q equal to it. Both the methods are quite sensitive and rapid and accurate. So these are the advantages of these two methods. And what are the theory behind your electrogravimetry? Here what happened, as I already said, that always according to the new rule of IUPAC, we have to follow the reduction part or reduction reaction of every electrode to establish the reaction as well as the mechanistic approach of the approach of the process. So here M2 plus ion gain 2 electron to give metal solid. So therefore the electrolysis, this is in your the electrolysis, it is the coulometry. So in the EMF, the electrolysis equal to EMF of cathode and EMF of your anode. EMF equal to your electrode potential, the reduction potential. The electron deposition is governed by Ohm's and Faraday's law. That is, um, in ohms, it is equal to it is equal to V equal to IR. And according to Faraday's law, it is equal to the amount of substance deposited or liberated during electrolysis directly proportional to amount of current or amount of electricity passed through it. So this is Faraday's law. So both these laws will be the theoretical approach to this to these theories, that is electrogravimetric theory and coulometric theory. Then we have, so this is E equal to IR. This is the EMF or E cell, that is equal to current into resistance. So this is equal to E equal to IR. So we have the equation, the electrolysis EMF equal to E cell minus IR, because this will be calculated from by using the Nernst equation, that is E equal to E0 minus 0.0591 by N log product by reactant. So this will be 1 by M2 plus N concentration, minus IR. So IR will be equal to the E. So E cell will be equal to E cathode minus E anode. This is already we have this equation, E cell equal to E cathode minus E anode. So E applied equal to E cathode minus E anode. Here it is put E cathode minus E anode minus IR. So where I equal to minus E applied by R plus 1 by R E cathode minus E anode. This is equal to I, or I equal to E cell minus E applied by R, and I equal to minus E applied by R plus K, where K is a constant. So by using this standard equation, we can calculate both the current as well as the resistance of the cell, and this is known as the current to applied electricity plot. So here a plot of the current of the applied potential in an electrolytic cell should be straight line with a slope of a negative reciprocal of the resistance. Here it is slope equal to 1 by R. So this is for a electrolytic cell, which is just the reverse of your galvanic cell or electrochemical cell. And you should know that in electrolytic cell what happen, the electricity is generated by your, sorry, in electrolytic cell chemical reaction is carried out with the help of electrical energy. So type of electrogravimetric method, we have two types, that is constant current electrolysis and constant potential electrolysis. So here what happens, is the electrolysis by which is your based on your Faraday's law, but here the current is constant, that is I is constant, and here V is constant. Okay, so the first type, that is I is constant, that is constant current electrolysis. The same figure is here, that is this is a platinum where anode, or generally the platinum wire is taken, and with the help and one platinum gauge is there, net like structure. Then it is dipped in the sample solution with a potential difference of 6 volt. That is just same as a battery used in electric torches. Then uh, we have a motor here, that is known as magnetic stirrer is also can be used, or a motor is used with one stirrer, that is mechanical stirrer. Then by applying the current and by controlling the voltage by the register, we will the metal dissolve in the sample solution will be deposited at this cathode, platinum gauge cathode, and the weight difference will be the amount or the weight of the weight of the metal present in the sample solution. Then you have potential constant. Then in this type of electrogravimetry, what happened, the potential remain constant. That is, in this method, the potential of the cathode is controlled. It consists of two independent electrode circuits that are connected with a common electrode. For the better result, three electrode systems are used, that is working electrode, counter electrode, and reference electrode. So here one extra electrode is used, that is the reference electrode is used, which maintains the fixed potential despite the change in solution of the components. That the role of reference electrode is to maintain the potential fixed despite the change in solution components. So electrode used in the electrogravimetry, we have uh, the following the electrode used in the gravimeter should have possess the following characteristics, that it should not be non-reactive. So generally non-reactive metal or noble metals generally used for this purpose. And we have it should be readily, it will be not, just wait. So next part will be uh, that is, it will be of two types, that is constant current and constant potential. So when current is constant, we have to use one reference electrode, sorry, we have the current constant by using the we use one resistor to control the voltage. And we have the constant potential, that for this purpose we may use one reference electrode. So this is just the connection of your electrogravimetric apparatus with constant potential. Then we have a reference electrode here, which maintain the constant potential. This is the counter electrode, and this is the working electrode. So this working electrode, the metal ion is deposited or also acts as the cathode, and this counter electrode, that will be the anode. So from which electrons are generated or oxidation takes place here. and here reduction takes place. So the metal in the solution gets deposited by reduction method in this on this cathode, and this will be connected to your current meter or ammeter followed by DC power supply. So this will be the current supply, and this will be the working mechanism. And just remember, this reference electrode is used here to have the constant potential. So for this purpose, the reference electrode is used irrespective of the change in solution component. So as this component of the solution changes, but due to the presence of this reference electrode, it will maintain the constant potential environment. Then we have what are the electrodes characteristics used in electrogravimetry. It should be non-reactive. It is very much a general thing that the electrode generally remain inert to the applied field or the solution we take. It should be what happened today. Students are calling. Just wait. Hello. So students, many students from your program just contacted me. Two students right now that they are unable to join today's class. Is there any problem in our online platform or anything else that students are facing this type of problem? But in our previous classes, this type of problem is not there. Actually, I do not have any access to your joining to this class. So, like you, I am also a participant to this class. So, these are all monitored and controlled at regional center, IGNOR regional center, Bhubaneswar. So, right now, I am just end my session here. Then after 2 to 3 seconds, I will again rejoin, and you all are again advised to rejoin that class for joining of the other students. Is it clear or not?
Okay, sir.
Okay, so Nagesh, Mahadev, Mahendra, then Akarshan, Abrar. So all are just you just left out and then again rejoin. Okay.
Okay, okay, okay.
Okay, sir.
Okay, sir. Okay, sir.
Nazrul, please mute yourself. Nazrul. Is it visible, students?
Sir,
Sir.
Okay, okay. Thank you. Uh, so up to this we have covered up, that is electrogravimetry and coulometry. And in the first part we have electrogravimetry analysis or electrogravimetric method, in which generally the metal ion dissolve in a solution or an analyte solution is separated gravimetrically. Gravimetrically means by weight it is separated, or this is a quantitative approach for the separation of dissolved metal ion solution. So in this part we used generally we use noble metal, that is the platinum, both as cathode and anode. Platinum cathode is used as a platinum gauge. The gauge means it is just a net like structure, and platinum anode, this is just a wire, that is platinum wire. This is used on platinum anode, and both these are connected through one the external battery, and due to the potential difference of around 6 volt, and by maintaining the control voltage with the help of a resistor, uh, the metal ion dissolved in the solution gets separated, and the pre-weight and post-weight of the uh, platinum gauge cathode is determined, and the difference in the weight will be the amount of metal ion present in the solution. That will be the electrogravimetric apparatus. And there will be two types of electrogravimetric apparatus, that will be at constant current and at constant voltage. So the constant current is mm, this type of this in this type, that is constant current electrolysis or electrogravimetry. What happen, a resistor is used, and this will be connected to a 6 volt battery. So the and with an ammeter, the current will be maintained at a constant value, and by changing the potential we will have the deposition of the metal ion in the cathode compartment, that is the platinum gauge. And second thing, we have constant potential electrolysis. And how we can have the constant potential, we will use one reference electrode, which is important, or which is used here to fix the potential despite of the change in solution component. So here what happened, three types of electrodes are used, and this one is the working electrode, and this is the counter electrode, and the third one is the reference electrode. So this reference electrode is used to maintain the potential fixed, that is constant potential. And the working electrode is the cathode, where the metal is deposited, and it is estimated gravimetrically, that is by weight determination. And this is the counter electrode, means this is the anodic part, where the oxidation takes place, and there is be liberation or generation of electrons are here. So electrons are generated here, and metal is deposited here, and these are connected through ammeter and direct current supply. This will be the constant potential electrolysis in electrogravimetric apparatus. So what are the characters of your electrode used in electrogravimetry? This will be, just wait, hello, huh. So here what happened, the electrode must be inert, and second one is it should be readily ignited to remove the organic matter. The commonly used electrode is the mercury cathode electrode for the deposition. So these are the primary characteristics of your electrode used in electrogravimetry. Okay. Then we have the next part, that is the what are the advantages of this? it forms the amalgam with number of metal. Amalgam means uh, it is just a complex or a compound formed with the mercury. This will be the amalgam. So, so this will be the amalgam with number of metals. That is, it will form a compound that is known as mercury amalgam. Mercury cathode is prepare form amalgam with other metals. It has a high hydrogen voltage. Then we have in this method the precipitated elements are dissolved in the mercury, and this method is mainly used in the removal of reduced element. So this is generally used for the removal of reduced elements. So what is the construction here? Here this is the cathode, and this is the mercury cathode, right? This is the stirrer, and this is the solution, and this is the outlet, and this and stirrer anode, and this is mercury cathode. Both these are mercury cathodes. This will be connected to that solution, sorry, connected to the external electric field. So what happened? Okay. So this will be the mercury cathode, and stirrer will be acts as the anode. So this will be the electrodes. We also have the PDF issued by your IGNO. Just after this, just we will look after this PPT first, then we will move to that PDF. What are the application? Generally, copper is estimated. This is a very common method for the determination of amount of copper present in a solution or a metal alloy. So this process is generally very much common in the industries, metal industry or alloy industries, where estimation of metal is very important. So for this type of elements, copper, bismuth, lead, cadmium, zinc, and tin, this electrogravimetric approach is there for the gravimetric determination, used in the simultaneous deposition of the metal, then used in the electrosynthesis, used in the purification process by removing the trace metal from the sample. Then we have colorimetry. This method is a measurement of the quantity of the electricity. This is mainly estimated by the reaction of the electrode. So this will be just an alternative to our ammeter. Okay, like where current is measured in colorimetry or colorimeter, the total electricity will be measured uh, mainly from the reaction of the electrodes. This is again of two types, that is controlled potential and control current. And in control potential, constant potential is maintained, and in control current, the current is maintained throughout the electrochemical cell. What is the theory behind this? The colorimetric methods are mainly based on the measurement of the quantity of the electricity. This is the measurement of the quantity of electricity in coulomb. That's why it is colorimetry. A sample which is to be determined undergoes the reaction at the electrode, which is measured at the electrode. The completion of the reaction is indicated by the decrease in the current to zero. So in colorimetry, when the current decrease to zero, that indicates the reaction is completed. This can be measured by colorimeter. The substance which is to be determined is first electrolyzed by the constant current. Then the total current is determined by the equation total current is product current into time. So these are the some specification as well as some equations related to our colorimeter. So this is the principle, that is Faraday's first law principle, where we can determine the W equal to mr into q by 96500 coulomb into n, or 96487 n, where n is where small n, it is the number of electron transfer, Q is the amount of electricity, Mr is the molecular weight, and W is the weight of the substance deposited. This is the molecular weight, and this is the weight of the substance deposited. So coulometry uses a constant current source to deliver a measured amount of charge. 1 mole of electricity, that is 1 Faraday. It is 964,485 coulomb, and this will be the construction or one figure of your electrochemical cell, where this is the auxiliary electrode, this will be the freed analyte solution with precursor generator electrode, then these are the current source, and these are some points that is due to concentration polarization will be there. This is in our PDF. We will go through this in details. The concentration polarization means this is due to the over voltage. Sometime what happen, the cell becomes a little bit hot due to the when the applied current is exceed the limiting value, then there will be over voltage will be there, and there will be polarization of the current. So this is known as or there will be polarization current as well as polarization of the concentration. So due to concentration polarization, it is very difficult to complete oxidation or reduction of a chemical species at any electrode. Coulometry is therefore usually done with an intermediate reagent that quantitatively react with the analyte. So the intermediate reagent is electrochemically generated from an excess of a precursor so that concentration polarization doesn't occur. The point at which all the analyte has been converted to a new oxidation state is called end point. So like in our titration, there is end point. In coulometry, there is also end point which can be traced out by the reading of that coulometer. So here what happened, when the new oxidation state is attained by a metal ion, then there will be change in current, or it may be the end of the reaction. The current will be zero. That means it will be the end point, and is determined by some type of indicator that is also present in the solution. The analyte concentration is calculated from the reaction stoichiometry and the amount of charge that was required to produce enough reagent to react with all the analyte. So this also depends upon the analyte concentration. So what do you mean by concentration polarization? It occurs when the concentration of a specific component increases. Concentration of a specific component increases or decreases at the boundary layer close to the membrane surface due to selective transport through the membrane. So this is known as concentration polarization. That in a solution medium, when a specific component concentration, it may increase or decrease where the boundary layer close to the membrane, that is just same as the liquid junction potential, where the two electrolytes or the oxidation half cell as well as the reduction half cell meet, that is zone of contact, a liquid junction potential, this will act as a membrane. And uh, when at the vicinity of that membrane, the concentration either rises or downs, that increases or decreases, there will be polarization of the concentration will happen through selective transport of the ions through that liquid junction potential. This will be the concentration polarization. So this will be the end of this ppt, and we will have our pdf here. So I will not go through that your introduction part, but our objectives are the principle of electrogravimetry, which we have already discussed. That is IR drop, that is related to your Ohm's potential, that is E equal to IR. Now this happens due to polarization or electrodeposition. So electrodeposition is related to electrogravimetry, and polarization it is related to your coulometry. Calculate the potential of a given cell to initiate deposition of metal ion, and calculate the residual concentration of the ion in solution before the commencement of the deposition of the next ion. Describe constant current and control potential electrographically. Explain the importance of control potential electrographically in the successive deposition of metal ions. Describe colorimetry and list the different type of colorimeters. And we will have the different type of colorimeters in this PDF. Then describe potentiostatic colorimetry, its instrumentation. Describe amperostatic colorimetry. Explain the method of in situ and external generation reagent in colorimetric titration. Explain the advantages. Okay. So in electrochrometric apparatus, it is just same as a Daniell cell, that is electrochemical cell, where external current is or external electricity is used to chemical energy or to initiate a chemical reaction, that is oxidation as well as the reduction. The same principle applied here, that is left oxidation, anode and negative. So here the in anode what happened, there will be negative sign like galvanic cell, and the cathode have the positive sign like the same galvanic cell. So here if copper gets deposited, then what happen, oxygen will be evolved at the anode. Then the cell is represented as copper slash copper 2 plus means it is in the solution state, double slash means it is the bridge, salt bridge, and where there is 2H plus and half O2 and platinum is the electrode. So here oxygen will be liberated at anode and copper is deposited at cathode. The net equation will be copper 2 plus reacts with water to give copper solid, that is copper metal, plus half O2 at anode plus H plus ion in the solution. So the cathodic reaction will be copper 2 plus to copper 0, and the anode there will be mercurous oxide. This is as a mercurous oxide, it will be 2H plus half O2 plus U2 plus. Okay, so there will be liberation of half O2 and 2H plus in the solution. Okay, this will be acts as just like a reference electrode, mercurous oxide, sorry, mercuric oxide. Then E cell, as we have already discussed in the first part, E cell equal to E cathode minus E anode. That will be in reduction potential, and this will be the electrolytic cell, where current is or electricity is produced from chemical reaction. This is just one ammeter, where here it is 2.35 milliampere is generated. Then this is the IR drop, where this is just followed the Ohm's law, that is E equal to IR. So why this IR drops? Due to polarization, when the applied potential or applied current is exceed the maximum limit value. Okay, just see here this one. What happened here? This is the current versus applied voltage plot, and the first one is the electrolytic cell, where where electrical energy is changed to chemical energy, but in galvanic cell chemical energy is changed to electrical energy. So this is the galvanic cell. So here what happened, when we applied voltage is excess, there will be the linearity is not maintained, it will be deviate, and this deviation, that is minus 0.04 volt, is our over voltage. Like in our galvanic cell, when output potential is exceed the limiting value, then the linearity, this is just in the opposite direction, that is this is from nearer to zero, this is far from zero. So this will be the linearity, and this will be deviate. This is known as polarization, and this will be minus 0.03 volt polarization, that will be due to your over voltage. So then E applied equal to E cell minus IR minus over voltage. This will be the net equation. Then we have polarization concept. So in polarization, what happen? This will be the uh, ohmic region. This is the straight line. That means it is E equal to IR. This is E equal to IR plot. Then what happen? This linearity is now deviate due to polarization or due to over voltage. And this point of deviation is known as onset of polarization, and this is the deviation. That means this difference between the linearity and the limiting current, this is known as the over voltage. And this is just a plot between current in milliampere versus applied voltage V. And there will be concentration polarization also there, as already we have discussed that that when excess or applied voltage exceed the limiting value, then through the membrane, that is through the liquid junction potential, or through the point of this is known as a zone of what is that known as, that is a liquid junction potential, that is which is acts as a membrane. So the concentration in the vicinity of the membrane may increase or decrease due to the over voltage or the applied voltage when exceed the limiting value, and this will result in concentration polarization. That means concentration varies with applied voltage. Then we have three surface phenomenon, that is diffusion may happen, migration of the ions may happen, and convection, this may be happen. So concentration polarization arises when the effect of diffusion, migration, and convection are insufficient to transport the ions at a rate that produce a current of desired magnitude. So this is the reason why concentration polarization is supposed to be happen. Then there will be kinetic polarization, means there will be effect of applied current or applied voltage to the movement or the kinetic of that of the ions. Kinetic or chemical polarization. So how many students have joined? Only 9. Okay. So kinetic or chemical polarization may occur due to change in chemical nature of the electrodeposition of another metal, or due to the coating of the electrode with a layer of gas such as hydrogen or oxygen. Kinetic polarization may also be caused by formation of film. This is just like a membrane activity on the electrode. An example of aluminum anode is liable to be passivated by a coat of alumina on it. So this is the kinetic polarization. To avoid the polarization, the aluminum anode is coated with alumina that will stop the kinetic polarization. And then we have kinetic polarization is most pronounced in electrode process that yield gaseous product. This is known as gas over potential. So you have to remember this thing. Gas over potential depends on several factors like electron material, current density, temperature, pH. Over potential for many metal differ. The voltage over voltage at a given current density decreases as the electrode surface is roughened. So these are just the surface phenomena. Then importance of over voltage, the existence of over voltage explain numerous phenomena. In a lead accumulator, during charging, the metal is deposited on the cathode instead of hydrogen being involved due to high over voltage of lead. Then it is possible to deposit electrolytically the metal which have a more negative potential than hydrogen, such as zinc, cadmium, tin, from an acid solution because of high over voltage of hydrogen on such metal. So these are just the applications. Okay. Also over voltage, that means the traditional or regular mechanism will be reversed when over voltage situation happen, that which gets deposited at cathode, they will be evolved at anode, and which are evolved at anode will be deposited at the cathode due to overvoltage. Overvoltage plays an important role in the industrial production of chlorine and sodium hydroxide by the electrolysis of brine sodium chloride solution. When electrodes of high overvoltage are used in electrolytic reduction, it would mean to increase the reducing power. Electrode with high overvoltage like lead instead of platinum are used in organic electrolytic reduction to get a desired product. So these are the applications. Then type of electrolytic method we have already discussed, that is constant current electrolysis. This one platinum gauge, platinum electrode. We have one stirrer or motor here which is connected to an external electricity of 6 to 12 volts. So here current is maintained fixed, and by varying the potential difference we will with the help of a resistor uh, the deposition will be carried out. Then physical characteristics of metal deposition, then we have this one. Then potential changes during the electrode at constant applied potential. So this is at a constant potential by using one extra reference electrode, that is generally mercury oxide electrode, which is acts at cathode, and the stirrer is acts as anode. Already we have discussed this one, and this the concept of concentration polarization will be supposed to be happen at cathode due to that membrane concept, that is liquid junction potential. Then we have this table, that is constant current electrolysis. The analyte is silver plus, that is silver, let us silver nitrate, and it is deposited at cathode, that is at platinum gauge electrode, that is as silver. Cathode is platinum, anode is platinum, and the medium is alkaline cyanide. That means silver is converted to silver cyanide. Similarly, cadmium cyanide, copper, it either copper sulfate or copper nitrate, and the electrodes are same. Just remember these things. In this electrogravimetric type, both the cathode and anode both are same electrode with different potential. So if there is different electrode potential, then one is acts as anode and one is acts as cathode. Then for bromide, it will be silver bromide anode, platinum and silver may be used. So these are the things. Then constant potential electrolysis, this is already discussed, where potential is gets fixed, and this is the system, and that is, this is the reference electrode, this is a counter electrode, this is a working electrode, this is a digital voltmeter, DC power supply, electrolysis. Here the electrode reference electrode acts as the role. The reference electrode role is to maintain the constant potential environment. Then we have this one, change in cell potential versus current plot. This is cell potential current with a time. So you have to remember this plot. Okay, so how this will be increased when when time increase, the cell potential also gradually decreases. And these are the electrode, that is mercury cathode electrode, this is already discussed. This is mercury cathode, and this will be stirrer, that will be the anode, and this will be the solution. It forms amalgam with a number of metal. It has a high hydrogen over voltage, and hence no hydrogen evolution even at high potential. So when over voltage concept is there, the gases which are supposed to evolve at anode will not be evolved, and they will be intact with this solution. They will be not separated. Okay. Then successive deposition of the metal, one by one the metals gets deposited, depending on their standard reduction potential. Okay, like uh, that is cadmium and zinc, ammonical cadmium and zinc. So they are deposited successively at minus 1.2 volt and minus 1.5 volt. So first cadmium will be deposited followed by zinc. Okay. So this type of things are there, the deposition of the successive metals, then preparative organic chemistry. So application of controlled cathode potential electrolysis, that is copper. If it is platinum electrode, the condition is like this. This is already discussed. Then we have second part, that is coulometry. This is based on your Faraday's law. So we said the quantity or the amount of substance deposited or liberated during electrolysis is directly proportional to amount of current passed through it. It is the Faraday's law. So according to Faraday's law, M proportional to Q. M is the amount or mass of substance deposited. Q is the electricity, which is Q equal to I into T. So M proportional to IT, M equal to ZIT. Z is a proportionality constant, or otherwise known as electrochemical equivalence, ECE. So how to define Z? So when I equal to 1, that is current equal to 1 ampere, and T is equal to 1 second, then M equal to Z. That means the amount of substance deposited or liberated at their respective electrode during electrolysis when current of 1 ampere is passed through for 1 second. The amount of substance at that moment is known as electrochemical equivalence. So when I equal to 1 ampere and T equal to 1 second, M equal to Z. So that means at that condition, electrochemical equivalence Z is equal to amount of substance deposited, that is M. So what is second law? Second law is uh, when when two or more um, two or more electrolytic cell, electrochemical cells are connected through series, the amount of substance deposited or liberated is equal to their equivalent masses. This is the thing when they are connected in series. So when I connect copper cell with silver cell with zinc cell in series connection, then what happen? The copper deposited at their electrode is equal to their equivalent mass. Similarly, for silver, it is the equivalent mass of silver, and for zinc, it is the equivalent mass of zinc. So finally, we can write M1 N1 by capital M1. This is a equal to M2 N2 by capital M2. So where capital M is the molar mass and small m is the mass of substance deposited into n is the number of electron transfer. So that means a small m is the mass of copper deposited into 2 divided by molecular mass or molar mass or atomic mass of copper. Similarly, this is for your silver, that is mass of silver deposited into number of electron transfer is 1 in case of silver, because silver is always Ag plus divided by molecular or atomic mass of silver. So here it is written mass of copper deposited into 2 divided by molar mass of copper equal to mass of silver deposited into 1, because silver will exchange one electron with other. That's why it is 1. But copper exchange will be number of electron exchange is 2. Molar mass divided by molar mass of silver. So as Q equal to current into time, where the electricity unit of Q is coulomb. Then we have Q equal to 2 into 10 20 coulomb here. This is just one problem here. Then then what is Faraday? Faraday is just 1 mole electron. The electricity carried by 1 mole of electron is known as Faraday. So it is 1.6 into 10 to the minus 19. It is the charge of 1 electron, and 1 mole contains 6.022 into 10 to the 23 number of electron. So by multiplying these two, we have 96485 coulomb, which is approximately equal to 96500 coulomb. So this factor, that is 96500 coulomb, it is popularly known as Faraday, to honor the father of electrochemistry, Michael Faraday. So now consider this reaction again. This is a reduction reaction. Mn plus 2 plus n electron gives m. So here m is the mass of substance deposited, m is the molecular mass of that substance, q is the electricity, then 96500 is the coulomb, and n is the number of electron transfer. So then if I replace q by it, then it will be mr into it divided by 96500 into n. So uh, this much amount of mass will be deposited by passing of the quantity of current, that it depends on the how much current is passed for how many minutes or seconds or how many times. This will be the m. So coulometry principle is just the overview of your Faraday's law, that is electrolysis. Then we have what is coulometer. So this is a device, here it is written, it is a device used for measuring the quantity of electricity required to bring about a chemical change of the analyte. It is usually practiced in coulometry to substitute the ammeter, which measure the current in electrical experiments with a coulometer. So this is just a substitute to ammeter. Here it is written, it is a substitute to ammeter. So coulometer is a device that will determine, or that will measure the amount of current or an amount of electricity required amount of electricity required to carry out the chemical reaction. This will be the function of coulometer. Then it is followed by gasometric coulometer, hydrogen oxygen coulometer here, where the anode and cathodes are like this. This is 50 centimeter long, diameter 2 centimeter. Two platinum sheets of 1.5 square centimeters are here, joined with a stout platinum wire serve as electrode. This is then a calibrated tube, that is glass burette, is connected to the electrolysis tube by means of pressure rubber. This is a pressure rubber, and is capable of moving vertically so as to adjust the pressure. Then 0.05 molar solution of potassium sulfate is used. So these are the instrumentation part of your hydrogen oxygen coulometer. Then the reaction is at anode, hydroxyl ion will liberate. At anode, oxygen will be liberated, that is formation of water, and at cathode, hydrogen gas will be liberated. Overall reaction will be H2O change to 2H2 plus O2. Here 2 moles of 3 mole of gases are liberated from 2 mole of water. So there will be 3 moles of gases are produced by consumption of 4 Faraday, which is equivalent to 0.1741 centimeter cube at NTP of mixed gas per coulomb. So lignin and lephid found the actual volume. So these are the historical things you should learn yourself. Then we have height, and this one is the nitrogen gas evolved at the anode, that is hydrogen nitrogen coulometer. In 0.1 molar hydrogen sulfate is NH2NHSO4. This is hydrogen sulfate that used as electrolyte, and this is hydrogen nitrogen. This will be hydrogen oxygen, the hydrogen nitrogen. So this is N2H5 plus hydrogen change to nitrogen, that is at anode, and cathode there will be evolution of H2 hydrogen. So the net reaction will be N2H5 plus change to N2 plus 2H2. And here the current density range is 0.1 to 0.007 ampere per centimeter square, and we have some precautions here. The burette should be water jacket, and temperature reads should be within plus or minus 0.1 degree centigrade. The electrolyte must be pre-saturated with oxygen and hydrogen. During the course of the reaction, the gas burette must be lowered periodically, and these are the things will be there. Then silver colorimeter. This is a silver colorimeter here. Silver nitrate solution is here, and this is the cathode. That is silver disc is the cathode, and silver is the anode. Okay, silver nitrate, silver anode, and silver disc is there. So here, the most satisfactory, the silver colorimeter is example of gravimetric colorimeter in which amount of metal deposited cathode or the metals stripped from the anode is determined. The silver colorimeter is the most satisfactory either the cathode deposition mode or better still in the anodic stripping mode for chloric and acid media. The same thing here. Okay, 1 molar silver nitrate is taken in the standard state, then a rod of pure silver enclosed in a porous spot acts as anode. So this is acts as anode. This one, this is porous. Then we have 1 milligram of silver, and this should be considered as a reference to electrode size. Also, these things are very much same as your general electrochemical cell. Okay. Then iodine colorimeter, colorimetric colorimeter. So this is in iodine colorimetry we have thiosulfate or arsenic 3 solution. Remember these names. Then colorimetric colorimeter. This principle developing a colored species. This is developing a colored species with a reagent. For example, colored species for cobalt ion is a nitroso R salt. This is the chemical used to color the cobalt ion with a measurement of absorbance with a spectrophotometer is may be used. And another example is reduction of iron 3 cathode and subsequent measurement of absorbance by using the reagent 1,1-phenanthrolene. So these are the examples you should remember for colorimetric colorimetry. In radioactivity colorimetry, we have a radioactive isotope like silver 110 may be used. So colorimetric is broadly of categorization will be like this. Colorimetry, constant current colorimetry, that is constant current means it is related to your ampere. So this is amperostatic. Static means constant, ampere means current. So this is amperostatic colorimetry. And this is control potential, or this is potentiostatic colorimetry. So one is constant current, another is constant potential. So if it is control potential, it is known as potentiostatic. If it is constant current, it is amperostatic. And amperostatic is again of two types, primary and secondary. The secondary is again of external generation analysis and internal generation. And then controlled, it is primary, only primary type, that is primary colorimetric analysis or colorimetric titration. Then we have constant current colorimetry. It is primary constant current colorimetry. In this technique, the element is to be estimated undergoes direct reaction at the electrode with 100% efficiency. That is this is direct reaction. That is constant current means it is just like the electrogravimetric. The platinum gauze and platinum wire is used as cathode and anode, and direct current is applied, and the metal ion dissolved in the sample solution gets separated, and the estimation is by weight, that is gravimetric estimation. Then in secondary, what happened? This method has enjoyed wider application and is frequently called a colorimetric titration. This is secondary type. This is titration type, where one of the reactant, that is a titrant, is quantitatively produced, generated at electrode which then stoichiometrically react with the analyte and to be estimated. For example, when iron 2, when oxidation of iron 2 is happen in platinum anode, we have iron 3, the primary anodic reaction. So this is a reaction happen in anode, that will be oxidation of ferrous to ferric. Then at constant current, towards the completion of the reaction, the water, from water what happen, oxygen gas will be liberated at anode, and there will be liberation of H plus simultaneously. And in the similar way, cerium also get oxidized to cerium 4 plus plus electron. So the net reaction in coulometric will be cerium 4 plus plus Fe2 plus. It will be Fe3 plus for cerium. This cerican produced by the oxidation of serious ion at the anode diffuse out and react quantitatively with ferrous ion. That means this cerium 4 plus, which is diffused out at anode, is again quantitatively react with the ferrous ion, which converted the ferrous ion to ferric. This net effect is an electrochemical oxidation of iron 2 with 100% current efficiency. That means here the secondary the secondary mechanism is happening. How? The cerium is the secondary element present here, and our primary element is iron, which we are looking for the concentration of iron plus 2 present in a given sample. So how to determine then? We were introduced the cerium 3 in excess. So where cerium 3 is excess, then what happens? Cerium 3 will change to cerium 4 plus by oxidation, and this cerium 4 plus, which is the secondary ion, is gets reacted with the primary ion, that is Fe2 plus, to convert it to ferric ion. So this is the secondary type mechanism. Then control potential coulometric analysis, where potential is controlled. The current is initially high but decreases rapidly and approaches zero at the completion of the reaction when the potential gets fixed. The quantity of electricity is most commonly measured with an electronic integrator or from the reading of coulometer. Then what is the special features? Coulometric method give more accurate and precise result than classical method. These methods are suited for both routine as well as a rare analysis, which involve electrolytic method of determination. Coulometric titrations are more popular and have the special advantage in the sense that the tedious steps of preparation, storage and handling of standard titration are avoided. These are very very important. In our traditional titration, we have a preparation of solution, storage of solution, handling is very important. These steps can be avoided in coulometry. Titration, which cannot be performed by conventional method, can be easily performed by coulometric. Titration of hazardous materials like titration involving unstable or difficulty prepared titrant such as bromine, tin 2, titanium 3 in molten states can be performed. In situ generation of titrant, for example, electrolytic generation of iodine used to estimate hydroquinone, ascorbic acid, and this type of in situ titrants also can be done with colorimetry. Then constant current colorimetry has widely been used than the control potential colorimetry. Then at last we have control potential colorimetry, is quite sensitive method and has selectivity. So one of the important type of coulometry, that is control potential, that is potential constant or potentiostatic coulometry. This is very sensitive and also this has some selectivity. Then let's have the instrumentation part and what is the principle. And it has at constant or static potential. This technique is similar to electrogravimetry, where electrolysis is carried out at fixed potential. This is very important, at fixed potential. However, the former is more convenient than electrogravimetry method by the fact that the weighing step at the final stage is avoided. So, in electrogravimetry, where weighing of platinum gauge, that is acts as cathode, is a important step to determine the weight of metal ion present in the sample solution. But here, this weighing step is avoided. That is the initial weight and final weight. Hence, control potential technique can therefore be applied uh, to system that yield deposit with poor physical properties like antimony, and to reaction that do not give solid products at all. For example, electrolytic oxidation of arsenious acid to arsenic acid at a platinum anode can be carried out. So these things where the physical surface properties or physical properties of any metal is very poor, this type of metal also can be estimated through colorimetry. So these are the instrumentation, that is cell assembly here. Just I do not read all the lines. Just uh, let's have a brief look at this part. The electrolysis cell of potentiostatic colorimetry, working electrode, platinum gauge or mercury pool. So platinum gauge is just like your electrogravimetric type, and mercury pool is just like your constant potential electrogravimetry. Okay, so let's have this one. Starting from here, platinum working electrode is this one, and this I think this is working means it is the cathode. Okay, that means it is the platinum gauge. Then this is the stirrer here, which can stir the sample. Then Teflon cell cap. This is counter electrode, means this is the anode. This is also made up of platinum. Then we have plug here, Teflon plug, inert gas and waste. Then this is a platinum gauge electrode. Yes, this one platinum gauge electrode. That is the cathode. This is the salt bridge, and this is the standard calomel electrode that is used to fix the potential, or or used to maintain a constant potential. So these are the cell assembly. And here in mercury, what happened? This is a standard calomel electrode to maintain the constant potential. Then reference electrode and salt bridge tube. This is also mercury, and this is mercury oxide HgO. It is the solution, that is sample solution is here. This is the plug, mercury waste, platinum wire is here, mercury pool, porous Vickers tube here, counter electrode here, and Teflon cap, inert gas, stirrer. Just go through these things, and we have a potentiostat. A potentiostat, this is an electrical device which maintain the potential of the working electrode at constant level relative to the reference electrode. So this potentiostat will maintain the potential of the working electrode at a constant level relative to the reference electrode. So the equation is E2 equal to E1, E standard calomel electrode, which is plus IC plus RU, which is ESCE plus EC. Let's have the full form. EC is the cathodic potential. This is the cathodic potential, which is equal to potential between P and the working electrode. So these are the circuit diagrams. This is the reference electrode P, and this is the working electrode, means cathode. This is the counter electrode, means this is the anode. And we have the circuit diagram here. That is A stands for equivalent circuit. This is the equivalent circuit connection, and this is the B, that is the resistance with the cell, and this is practical circuit. This is the practical circuit. Then integrators are also needed for connection, and the equation is I equal to C into A, that is Q equal to I into T, where Q is the coulomb. So Q equal to I into T proportional to C into A into T. So A is the here I is the current and T is the ampere. What is C and A? Is it is a concentration, that is just C, and area, electrode area, that is A. So current is directly proportional to concentration of the solution as well as the area of the electrode. And as we know, Q equal to I into T. So I is replaced by C into A. So we have C into A into T. This is the total electricity Q. So application of coulometry in organic analysis, around 55 elements can be detected at the cathodic reduction part. Analysis of radioactive metals like uranium oxide to uranium 4 plus in acidic medium. These things can be done at minus 0.6 voltage and by using standard calomel electrode. And we have microanalysis also can be done. That is microanalysis means my analysis at microstate, that is 0.01 to 1 milligram. This will be the microanalysis. Then followed by multiple control potential analysis, multiple step, that is copper can be separated, followed by bismuth, lead, zinc, depending on its on their reduction potential. Then continuous monitoring of a gas stream, this can be done. Continuous monitoring of gas stream, that is if a porous silver cathode and cadmium anode is used, then oxygen uh, accept electron to give hydroxyl ion, and this hydroxyl ion will oxidize cadmium hydroxide, and liberation of two electron will be there. And this is the instrumentation for continuous recording of oxygen content of a gas stream. Just to go through these things, these are very simple things. Okay, here what happened, cadmium cathode will be there. At cadmium cathode what happened, this is the cadmium cathode, 25% potassium hydroxide, porous bubbler, and electrode is used silver. Standard resistors are there, and this will be the reaction, that is cadmium changed to cadmium hydroxide. Then electrolytic determination of organic compound. This is the compound electrolytic determination, that is trichloroacetic acid or acetation. Trichloroacetation will lose or will uh, mm, one Cl minus will separated, and we have dichloroion. This is a reduction at mercury cathode end. Then the electrolytic synthesis of a new organic compound. This can be also done. Determination n value, that is number of electron transfer by also from this. This is a picric acid, that is 2,4,6 trinitrophenol. It is known as picric acid. When picric acid, we will have a reduction, addition of H plus. Then this nitrate ion, that's NO2, gets converted to NH2 amine, or this is now 2,4,6 triamino phenol. And here there will be 18 electron transfer, and the n can be found to be 18. So this is another application or for perform your coulometry. Then constant current, that is amperostatic, and this is just a diagram of your coulometric titration by amperostatic, that is current remain constant. Here mercury electrode is used, current remain constant by external circuit. This is the electrolytic solution, counter electrode, and this is the filtered glass disc. Magnetic stereo will be here. Generated electrode will be acts as cathode, and stereo will be here. And the cell assembly is just like this. This is the circuit diagram. Okay, this is the titration vessel is here. Then one switch. Then these are type of circuit diagram. Okay, and here also platinum foil or platinum gauze with a large surface area is used for electrolysis. Then external general titrant, we have the reaction uh, as discussed, water gets treated to H2 at cathode and O2 at anode. So this is external general titrant, where the cathodic reaction is addition of electron and anodic wire will be liberation of electron, and there will be electrolyte solution from this reservoir here. This is the source of OH minus, because OH minus is generated here, and here is the source of H plus and H plus and be generated here. They will again combine or react to form the water again. So this will be the externally generated. Okay, so this is the external generation of titrant. Here also see platinum gauze is used, or platinum metal is used for both the electrodes, cathode as well as the anode. Detection of endpoint in coulometric titration. Endpoint, how to determine the endpoint? When the total electricity in the coulometer becomes zero, the reading, total electricity reading, that means there will be neutralization of the chemical reaction is happened. So there will be no further deviation, or there no further difference in cell potential. So this indicates the end point of the reaction, and there will be completion of the titration process. Then we have some spectroscopic endpoints. The exact endpoint can be determined by extrapolation of the linear portion of the titration curve before and after the endpoint. By proper choice of lambda max and molar absorptivity, the sensitivity and the selectivity of the method can be improved. So these things you have to remember. Then neutralization titration, we have this one: strong acid and weak acid. Precipitation and complex formation titration. Precipitation means like your silver in silver chloride. It is precipitation. Complexometric titration means it is just like complexion with EDTA, that is ethylene diamine tetraacetate ion. This will be your complexometric titration, where complex compounds are formed with multidentate ligands, like your EDTA, ethylene diamine. Here it is written ethylene diamine tetraacetate ion, EDTA. It is used for the complex formation. Okay, this is the reaction: mercury amine Y2 minus plus ammonium 2 electron, mercury 2 ammonia. Then this will have EDTA 3 minus. Then oxidation reduction. This is redox reaction. This is the redox reactions are supposed to be happen, and this is the acid base reaction. This is the precipitation reaction. Silver gets converted to silver chloride. Then this is the mercaptans. Then zinc, the generator electrode reaction is formation of iron cyanide. Then this hexacyanoiron gets attached to zinc to form this complex. This type of and this is one complex reaction with your EDTA. In an application, estimation of bromine, like your substance determined is arsenic, antimony, uranium. Then by the use of chlorine, we have arsenic free and iodine, arsenic free, antimony, cerium. For this type of ions can be determined. Then what are the advantages? Preparation, standardization, storage is not required. like traditional titration, easy to handle. A single constant current source can be generated. Colorimetric titration can readily be adapted to automatic titration as the current control is easily done. A number of automatic colorimetric titration readily available in the market to monitor the environmental pollutants. The chloride titrator silver ion is generated colorimetrically in sulfur dioxide monitors. Anodically generated bromine oxides the analyte to sulfate ion in carbon dioxide monitor, in which the gas stream observed in monoethanol amine is treated with colorimetrically generated base. In water titrators, Carl Fisher reagent is generated. Just try to remember these things, and this is all about your colorimetry part, the electrometric and with your colorimetry. Then our next unit will be application. Just I will uh, briefly discuss these things. Okay. So application part, we have degree of dissociation weak electrolyte, because strong electrolyte is 100% ionized. So for weak electrolyte, degree of dissociation concept is there. So what is degree of dissociation? The percentage or how extent a weak electrolyte is dissociate. So this is known as the degree of dissociation. So let us, this is a weak acid which is dissociates, and always you should you should write this equilibrium arrow, not a single arrow. Single arrow denotes the strong electrolyte, and double headed arrow denotes the weak electrolyte. This is reversible. Okay. So Ha is H plus A minus, that means it is partially dissociates. So at initial concentration is C, H plus ion concentration is 0, 0. Then at equilibrium, let us alpha is the degree of dissociation. Then C1 minus alpha, C alpha, C alpha. So what is the equilibrium constant? This will be concentration of H plus, concentration of A minus divided by concentration of HA. So this is C alpha, C alpha by C1 minus alpha. This is alpha square by 1 minus alpha. Alpha square by 1 minus alpha. So here finally what happened? Yes, this is same for your base, that is a BOH equal to B plus OH minus. Like your acid, this is also your base. It is C alpha square by 1 minus alpha. Then we have concentration is replaced by activity. The same thing written here. Then we have molar conductivity lambda m, which is equal to degree of dissociation alpha into, that is this is conductivity at alpha. So alpha equal to lambda n by lambda alpha, right? So these are the some equations. Then we have uh, conductivity or conductance versus your lambda c equivalent conductance. Then we have this type of readings are with us. Then this is the Pollard's law as discussed in previous class. That is the conductance at infinite dilution of a weak electrolyte. It is the conductance of the of the respective ions or respective ions, that will be acetic acid is formed when sodium acetate is added with hydrochloric acid and is subtracted with sodium hydrochloride. Then it is what happened? Chlorine cancels, sodium cancelled. So the remaining part will be CH3COOH. That means it is again the acetic acid. So acetic acid is a combination of sodium acetate plus HCl minus NaCl. So by putting the conductance values or molar conductivity at infinite dilution of sodium acetate plus the conductance of HCl minus conductance of NaCl, we have the conductance of acetic acid here, right? So this plus this minus this equal to acetic acid. So you have to solve these things by knowing the respective ions. So here CH3CO minus Na plus, this is H plus Cl minus, this is Na plus Cl minus. So it will happen Cl minus and here it is plus Cl, cancel. Na plus minus and here it is Na, cancel. So the remaining will be CH3COH. So these are the things will be there, and then the degree of dissociation will be 48.63, that is lambda m divided by, at infinite dilution it will be the degree of dissociation. Then ionic product of water, these are all class 11 12 things in our higher secondary level. So this is the ionic product of water, that is Kw equal to activity or concentration of H plus, concentration of OH minus. This is always equal to 10 to the minus 14. This is 10 to the minus 7 for H plus ion, 10 to the minus 7 for OH minus ion. This will be always 10 to the minus 14. And this is 1.12. It is generally taken as 1. So that's why the water is a neutral solvent. Then we have solubility and solubility product. Then this is also related to your equilibrium constant equation like this. Here the concentration of this will be HgCl divided by Hg plus and Cl minus. This is just a small problem here. Just go through these things. Then conductometric titration is an um, application of a conductometric part, that is titration. With the help of titration we can determine the concentration of precipitate salt like your silver. Then we have large conductivity of anion will be determined. Titration of a slightly ionized salt doesn't give good result, but conductivity increases continuously from the starting point. So these are the things you should learn. Then this is very important. Conductometric titration between strong acid and strong base. So first of all, what happens when a strong acid is this is volume of alkali added or base added, and this is the conductance part. So first of all, what happens? The acid is taken in the conical flask and the sodium hydroxide is added. Then gradually what happens? The neutralization will be happen. So H plus and OH minus will form water, and there will be neutral water will be formed, and the conductivity decreases because the number of H plus ion decreases. Initially there will be decrease in H plus ion number. That's why conductivity decreases to the end point. Then at this point where the number of H plus ion and OH minus becomes equal, then by adding the next drop of OH minus, there will be excess OH minus ion concentration in that solution. So then suddenly the conductance will increase. That means it is the plot of your strong acid versus strong base. So this is the first one is the strong acid, strong base, and this is for your strong alkali or strong base. So like this, again weak acid strong base means the weak acid concentration is gradually decreases at a point. This is the end point is now, and when the strong base sodium hydroxide is added, the conductance A is suddenly increases due to OH minus ion, highly conducting OH minus ion. So then strong acid weak base. So this is the strong acid gradually decreases as this is a weak base. So that's why it will remain parallel to the concentration of ammonia. So this is not not go up. It will be remain parallel because this is weak acid. Then weak acid weak base. This depends between weak acid and weak base which one is strong. If it is relatively the acid is strong, then the plot will be like this. If it is weak base, the plot will be like this. That means initially what happened? There will be increase in conductance due to dissociation, and this is the end point, and after that this will remain constant. Then if it is a mixture, then this is strong acid, then this is weak acid, and this is strong base alkali. So this is strong acid, weak acid, and strong base. Right? So displacement titration will be there. There will be displacement, then followed by precipitation titration. That is same as your silver chloride titration. This is the plot between your barium acetate. This is precipitation titration. That is ammonium sulfate with barium acetate. Then we have the last one, that is redox titration. This is the redox titration, that is permanganate with iron. The iron converted to ferric, and manganese plus 7 converted to manganese 2 plus. Then electrogravimetric, we have estimation of ions. We have discussed today this one at constant potential and constant current. Then where quantitative analysis is there. Then these are the things we already discussed. In separation, simultaneous deposition one by one. In preparative organic chemistry, these are the applications. Then application of colorimetry, we have in our application part, we have two things: control potential and control current. Then we have in our application part, we have supporting electrolyte, and this is the standard calomel electrode, and these are the elements which are used, or ions or reagents, for the determination of the these things, supporting electrolytes. Then general procedure for performing colorimetry term titration, this is already we have discussed in our previous unit. Separation of nickel and cobalt by, just go through these things. These are the procedure. The equation is same. That is, m is the amount of substance deposited, m is the molar mass, I is the current, T is the time, n is the number of electron transfer, F is the number of Faraday. Okay, multiple step control depend on the standard reduction potential. Then microanalysis, radioactive analysis, then continuous gas stream. The same things are repeated here. Okay. Then this is organic compound picric acid change to triamine phenol with n value is 18 electron. Okay, so n value is written the same thing written here twice. Then application of colorimetry, we have neutralization titration, we have acid base titration, then we have complexometric and precipitation titration, that is then followed by your precipitation with ethylene diamine tetraacetate ion. Redox titrations are there. Then these are the things, how species are determined, what are the generator electrode reaction and secondary electrode. Then these are the negative ions, or these are the oxidation reduction ions. Okay. Then we have what are the advantages, already these are already told to you in the previous unit, and this will be end of this unit, that is your electrogravimetric and colorimetry. So you have to remember the principle, the circuit diagram, and the cell construction, as well as the working principle, followed by the application, advantages and disadvantages. This will be very much helpful to you all, and hopefully today's class is very much easy to you all, because these are very much a common common industrial things which are carried out in metal industries or metal alloy industries. So if you have any doubt, or something you would like to say, you may. Uh, we have 5 to 7 minutes of discussion, and tomorrow we will have the next two units, that is unit 7 and unit 8. And unit 7 is all about your block 3, I think. Yes, unit 7. It is voltammetry. So voltage will be there with our polarography. And in unit 8, we have right, polarography and amperometric titration. So this is current based titration, and this will be a polarization or polarography. So, any question or anything else you would like to question or ask, or anything else you would like to tell? Over to you, students. Just go through this PDF. Your IGNO material is very good for technical as well as conceptual point of view, and it is not possible to possible to cover up all the points within 2 hours. Okay, we have only 7 classes for 13 to 14 units. So we have to finish at least 2 units per class every day. So that's why some things I intentionally skipped, and which are less important for you, and as suggested, you should learn and try to remember things accordingly for your theoretical exam. And we have also planning to conduct your practical classes after your theory classes, and this will be intimated to you through your mail. Okay, any question from anyone? Nagesh, Mahindra, Abrar, Nazrul, Akarsan, Mahadev, anyone? Okay.
Yes, sir.
Okay. Sir, if any DSC group created, just wait. Add me. If not created, send me your WhatsApp number. I can create an. Actually, Nagesh, already PGDSC group one WhatsApp group is there, which is in which I think most of the students are already added, and you may communicate them to add you to that group. Okay, so it is baseless to create more than one group for a particular program. So it is good to have only one group, and that group will be official, and we will share all the relevant things, materials with that group only. So I think for today's class, most of the students are not able to join, and in the mid of the session, I um, end the session and again rejoined. But after that also, most of the students are not joined today. So in this regarding, I will talk to regional center Bhubaneswar. What is the problem or any lacuna from what end? So I hope this type of inconvenience will be not repeated. Okay. Akarsan Misra, your number will be added, dear group. Yeah, so Abrar, I think, is the admin of this group. Abrar, Abrar is here.
Yes, sir. Yes, sir.
So who is the admin of
Yes,
our
sir.
PGDSC WhatsApp group?
Yes, sir. Yes, sir.
So just take a screenshot or photo of that of this group chat, and accordingly you are advised to add them in our PGDSC WhatsApp group. Okay.
Okay, sir. Okay, sir.
Okay. So thank you, students. We will meet tomorrow again at the same time, and let's learn something from nothing, and hope you will understand the things quite well. And we will have another 4 classes, and this will be the end of your PGDSC program. And after that, I will intimate you about the practical classes of PGDSC. So till then, thank you. So we will meet tomorrow. Thank you. क्या
Thank you, sir.
Thank
प्रैक्टिकल
you.
Sir. Thank
क्या प्रैक्टिकल क्लास ऑनलाइन होगी? यस यस यस, आकर्षण मिश्रा, practical class will be on online.
Sir,
सर
when will
ऑनलाइन
be
है।
the practical class will start? Hello.
अबर जी
Hello.
आपका नंबर सेंड मी थोड़ा।
ओके सर। नागेश। हेलो।
नागेश्वर राव।
नागेश चौधरी। चौधर। हेलो। हेलो।
नागेश चौधरी 960
जी यू कैन।
39।
जी you can send me text in WhatsApp. I can send WhatsApp link. आरक जो है ना, आरक्षम मिश्रा, प्लीज।
आकर्षण मिश्रा जी, आर यू देयर?